So whether developed or developing countries, it's always a huge investment with today's trend in like public-private partnership projects. Also in a lot of mining projects, you're always requested to have some sort of a rail spur or rail connection to be able to transport a lot of the products of like the mining processing in and out of the mining site. So in today's topic, we'll just start with a brief intro about like a typical railroad design and the main components we have. So we usually have a rail, like the rails placed over like the ties or the sleepers. And then we have what we call a track bed. This track bed is mostly known as a ballast, sub-ballast granular material. But as I'll show you guys throughout the presentation, there can be different formations and different types of track beds. And then those track beds will just transfer the load of the train into your subgrade. So the main components we have is the rail and sleepers, the track bed foundations, and this is where like your input would be required from a geotechnical point of view. And then your subgrade is basically your founding soil. One of the issues I always came up across when I'm reviewing work by others is sometimes you focus a lot on designing the track bed, but then people tend to overlook how these loads will transfer into the subgrade. So always remember that your subgrade is your founding soil. That's the soil transmitting, or this is the soil that need to be able to carry and sustain the load for like the design period of your railway embankment. So just an idealistic approach when dealing with this problem is you have traffic data. This is very, very important, very vital, because it means a lot of money. And this is one of the areas where there is always deficiency in information from usually the client side as to the expected traffic data. So it comes back to using common knowledge, engineering like knowledge, as well as digging up data when it comes to the expected traffic data for railway alignments with sort of similar properties and characteristics to the one you're dealing with. Soil properties, very important. You can achieve these by having an advanced and develop a proper field and laboratory testing. So know what you're doing, know what you're looking for, and select the samples that would be representative of your site so that you can have a better judgment on what type of material you're dealing with. Simulation, semi-empirical, there is a lot of semi-empirical approaches, whether it's numerical, so numerical softwares that are developed using semi-empirical methods, or advanced numerical methods, which again requires more sophistication. You need to deal with a lot more parameters, and you need to understand what's the significance of these parameters. And then your output is basically what you're hoping to achieve by the end of your design. So I'll just try to break down these topics and talk a little bit about each one. Again, briefly, I didn't mean it to be like an intense lecture, but the idea was to give you guys an insight as well as touch upon the key issues that you have to be aware of when you take a similar job. So the static wheel load is something that you usually get depending on the train type. So when we talk about trains, we're talking about locomotives, we're talking about the rail cars, typically that carries passengers or carries like freights along the rail track. Luckily, because it's a very standardized profession, I guess, the rail engineering, there is a lot of tables, there is a lot of manuals. Just to name few, the British Standard, the ARIMA, and the Canadian, like the CN rail standards, they provide tables that discusses the static wheel load depending on the load you have, depending on the type of train you're using. Then the impact factor, and that's when the empirical approach kicks in a lot of the manuals and the guidelines. And the idea is how to switch your static load into what we call a dynamic wheel load. And the purpose of the dynamic wheel load is basically to consider the fact that there is, it's a moving load. So it's something similar to the line of influence. For those of you who have interest in structures, probably came across this a lot. Or to consider the impact of the, magnification of the static load to encounter for the additional stresses due to the dynamic movement of your train on the track bed structure. Different wheel diameters. Wheel diameters are very important because they actually get into your impact factor, and the impact factor can vary significantly. So you need to be aware of like the wheel diameters that you're expecting on your rail track. I think a lot of studies have been done to kind of see what's the critical loading condition, and it was found that the condition that I'm showing here at the picture at the bottom, where you have basically 4 axle loads. So you count the wheels here, 1, 2, 3, 4. So each wheel is connected by an axle. So in that situation, this is the more critical criteria from a geotechnical and actually from a structural point of view when you're designing your rail embankment. So the maximum rail seat location, very important, and just keep this picture in mind, the 4 axles that we have here. Yeah, this one. Other 2 key factors also for the traffic data is the traffic tonnage and the number of repetitions. And I thought, this would be just an easier way to kind of go through them and see their significance. So typically in a wheel load for like some of the like common rail cars, you're dealing with 36 pound per wheel. So this is the static wheel load. And then for one car, you can see that given the critical scenario or the critical simulation of like loading on the embankment, you have 1, 2, 3, 4 times 2, we have 8 wheels. So this would be the total load that you have at the critical situation, which is equivalent to 140 ton per rep. The number of repetitions, you can assume that, just for simplicity, 200,000. And I use this just for the sake of the exercise, but usually you're able to, when you have rigorous traffic data, or when you're dealing with mining production, for instance, where you have a certain production rate per annum or per year, and you can know that how much the train can transfer per trip. So you can know how many trips that the train will take over your track. And this would be the number of repetitions. And then basically the multiplication of these two would give you the traffic tonnage, or the TI. Very important parameter. And it's very important because it helps you classify how critical the railway embankment you're dealing with. Usually up to 5 MGT, million gross ton, is considered like a light application track. Above 5 is considered like one of the more critical or heavy track application. So the second item that you need to also have before you start designing is the rail pressure on your track bed. Throughout like the different tasks I have handled, there is usually different methods to estimate that track bed pressure, mostly from the wheel load. There are a few programs, just to name few, like CanTrack, one of the readily available, easy to use tool to help you estimate the rail pressure. And in today's topic, I'll just touch upon 3 different methods in more details and show you guys the equations and what are the governing parameters. Keep in mind that our idea is we have train load. This train load is transferred through the rail track onto the ties, and then these ties transfer the pressure into the track bed. So just keep this in mind as we go through the presentation. The ARIMA, that's the the American Railway Engineering Manual. They provide plenty of equations to calculate what they call the ABP, which is the average ballast pressure. I picked one of the equations here because it directly correlates the ballast pressure to your wheel loading, your impact factor, and the distribution factor. And that distribution factor is basically to consider um, the fact that your wheel load will be distributed as a uniform pressure on your track bed. And then there is also another enhanced method in the ARIMA. And in this method, you basically consider the rail ballast interaction. And so this is sort of an advancement to the previous method. And if you guys use this method, the ARIMA, or you try and follow this method, you will always realize that this method gives you probably 25 to 30% lower pressure on the track bed, because it considers how the parts act together. Remember, you're designing a structure, although the rails are usually either typical from like the specifications, like the track specifications, or they come from like the structural slash rail team. Um, Keep in mind that the rail with the sleepers, they act as one body, and that body transfers the load into the track bed. So in this enhanced ARIMA method, it considers the rail stiffness and deflection under applied loads. And the way the load transfers is you have the P, which is our dynamic wheel load, the static times the impact factor, and then it travels to the ties, the horizontal sleepers we have here, and then from the tie, it goes to the top of your ballast layer. Just few simple equations here. Again, generic equations, but they just convey the message. You have a distributed pressure on the tie, and that would be the rail stiffness times the rail deflection. And these are rail stiffness. Again, there is a lot of um, interpretations as to how much would the rail stiffness be. There are a lot of field tests that are usually done, or typical rail stiffness that's recommended depending on the million gross ton per year that you're dealing with, which is the traffic tonnage. Your rail deflection, the output of this gives you a distributed pressure. Now remember that this pressure is uniform pressure. To consider a critical case, you need an influence factor, and that brings us back to the line of influence models, the fact that you have a single wheel moving along the rail track. So again, you rely on the manuals like ARIMA and see, how to get an appropriate beta factor to get your P max. And then this P max, when you multiply it by the tie spacing here, you're basically converting this into a load over your tie. So this is the pressure because you had that pressure linear, and then you multiply it by the spacing A, which is the spacing between the tie and the other tie, center to center. This converts it into a horizontal or into a uniform pressure acting on the sleeper. And then from that F max, you basically divide it by the area of the sleepers. And that schematic here hopefully explains things much better. But as you see here, you have a maximum pressure and you don't have a uniform pressure all over. You have an effective length of the tie that actually sustains the majority of the load. And then you have an area here where the surcharge significantly drops. So you divide your maximum force by the effective area and you get your average ballast pressure. So when you do this approach, the enhanced one, and you compare it with the old ARIMA method, you will realize that usually this method tend to give you 25 to 30%, at least what I have seen, for the average ballast pressure compared to the typical ARIMA method, although it needs more input. So, and that input is probably what makes it a little bit enhanced because it considers how the parts work together, um, and how they impact the pressure on the track bed. Now, when you have this load, which is the surcharge acting on your ballast, now you can start thinking about how the track bed will look like. So there is track bed type. This is something that you need to think of, you need to specify, and there is the thickness of each of these components. So the granular track bed is the traditional one. That's very common. Sometimes it's not very economically efficient. Just keep this in mind. So you have the ballast overlying the sub ballast, and then your subgrade. Now bedrock is not a necessity here. Sometimes a stiff soil compared to the overlying soil, or sometimes just the natural damping that would happen when the surcharge transfers the load with depth. So just this bedrock, don't think of it as a bedrock geologically, but it's more like a refusal surface, or a surface where the effective stress is not did not like increase significantly due to the overlying load from the ballast, sub-ballast. There is the asphaltic track bed, which is basically a ballast and asphalt binder that provides some tensile strength and distributes the load better onto the subgrade. So you basically substitute the sub-ballast with a layer of asphalt within your ballast layer. And then a combination, if needs be, you might have a situation where you have ballast intermixed with asphalt and then overlying a sub-ballast and a subgrade. So the type is, again, it's the cost, the lifetime of the project, and the specs or the specifications that you have for the project, and if it provides any guidance as to what type, and also the familiarity of the available contractors, like local contractors within the area you're working. The granular material thickness, again, plenty of equations. Uh, Interestingly enough, like the famous like Buzanisk equation actually provides a not so bad formula to get the granular thickness, and in most times the numbers you're getting from Buzanisk are quite close to other approaches. The one common method that's used, at least within like North America, would be the Talbot equation, and in this equation you have stress at the bottom of the tie, and you have the allowable subgrade stress. So this is your bearing capacity right there. So you're going to be aware of the soil conditions, and like what sort of strength that you're expecting from your subgrade to be able to get the support ballast. The idea is the thickness that you're using here will govern how the pressure will be distributed within your track bed. And then one of the methods that I think is one of the most like robust design approaches out there, and it touches upon few key concepts that we geotechnical engineers are always interested in when dealing with embankment design. It considers the impact of repetitive loading, and it's valid for soft grain subgrade. At least this is how they develop their approach. But with the right amount of data and the right information, you may be able to extend it, but be a little bit cautious if you extend it to other like not soft grained like silt clay and intermix, for instance, like glacial till and stuff like that. The good thing about this method, Lee et al., is it introduced also the serviceability and the plastic strain limits. And that's, again, concept that is not quite appreciated by other methods. So in Lee et al., you're dealing with two modes of failure. We have the progressive shear failure, and that's basically when the load is excessive compared to the capacity of your subgrade, and then you start forming this like rutting basically of your subgrade due to the excessive settlement and shearing along your subgrade. So it's very similar to like a bearing capacity failure. And the plastic deformation is the second mode, and that deals quite a lot with your serviceability. A matter of fact, sometimes when people overlook the plastic deformations along the rail track, and when they do maintenance, they keep increasing or adding more uh, ballast into like the fouled areas or the areas of deficiency or excessive settlement. And what this does is, because you've exceeded the plastic limit of your soil, you end up getting these like concave shapes vertically or like transversely, and also longitudinally along your track. You will have a Z shape um, of like ballast basically sinking into your sub ballast. The schematic talks about soft clay, but this is not necessarily even non-plastic silt with sand or stiff to hard clays. Again, if the thickness is not designed properly, the amount of loads that you can get here might be excessive. So the objective of this method is basically to estimate the granular material thickness that limits or that addresses two criteria: the plastic strains and the deformations. You want to keep them to an allowable limit. Now, the criteria for allowable strains and deformations, I personally like to link them to the stress ratio if we're dealing with soils in general. So how much deviatoric stress you're getting versus how much compressive strength you're expecting your soil to give you. And also there is like design codes, project specific standards, um, manuals that provide guidelines. And with guidelines, you have numbers to start with, but they are not necessarily. Sometimes they are stringent, more than needed, or sometimes they are a bit loose. So you need to just check what's your guidelines are, and the criteria that you need to pick your allowable strains and deformations. Just briefly here, if you want to design for like against mode 1 failure, which is the plastic strain, you want to make sure that the epsilon p, like the plastic strains you're getting on your subgrade, is lower than the allowable plastic strains that you specified. So um, this schematic here, you have the traffic conditions. So again, we talked about the wheel loading, we talked about the repetitive loading, and from that you get your design load and the equivalent number if needed. Equivalent number is used when you have a multi-purpose tracks where you have um, locomotives passing by, you have passenger trains, and you have also freight trains. So at that point, you kind of need to do a little bit more of digging to get an equivalent repetitive loading, considering how heavy and light each trip might be. Um, and then your design criteria is your plastic strains. And from your plastic strains, you can decide on an allowable um, stress ratio. Subgrade characteristics, we talked about this: soil type, your compressive strength. That's when your geotechnical sense, I guess, kicks in, and you have to pick up a number that you feel comfortable to load your soil to. Resilient modulus, one of the challenging parameters. There is a lot in the literature about the best way to simulate the resilient modulus. I haven't seen resilient modulus testing being done specifically. I guess part of it is it's very research oriented. So unfortunately, in the practice, people tend to get the resilient from some other parameters. But maybe something I came across was heavy correlations between the resilient modulus and the unconfined compressive strength. Um, and again, don't think about the unconfined compressive strength as test exclusively for like clay only. It can also be handy in an intermixed soils where you have enough cohesion and consistency. So you can always rely on this when you're dealing with silt clay or like silt clay like materials to get a sense of your resilient modulus. The granular material resilient modulus are usually um, given in your design specifications. These are target resilient modulus, usually significantly higher than the soils, just because of the crushed rock nature that you're dealing with for your granular material. You take all this, you have your allowable deviatoric stress. You go through charts. I'll show you this in a bit. You get your strain influence, and from there you can get your granular thickness. So the approach sounds pretty straightforward. However, you need to be aware of all the all the kinks and all the swerves as you develop these parameters till you get to your like granular material or granular layer thickness. This is where you have to do um, a little bit more interpretation and look at your data to be able to decide on which deviatoric stress you're comfortable with, how much would that mean in terms of strains and strain influence factor, and then what would be your granular material thickness. So this is just an example I digged from one of my old projects, but I basically, the equation they provided here correlates your plastic strain to the stress ratio. A, M, and B, these are your um, stress, shear strength parameters. Um, Lead L, they have done a lot of work as well, trying to specify, um, again, guidance as to how to get the A, the M, the B from a quite intensive database. The good thing is you can always have enough testing uh, from like your project specific testing, and you can actually extend on what they did to come up with your own parameters of A, M, and B. I'm not gonna touch on this, but they have a paper that's very detailed, and it can help you actually understand the significance of each of these parameters. Um, and then you see here with the stress ratio, you have a cumulative strain, right? This is basically a soil that's yielding, right? As we go with like higher stress ratio close to one, you're basically reaching the maximum capacity of your soil. You're getting a very high plastic strain. And you can say, okay, if I am comfortable with a stress ratio of half, so this means the deviatoric stress acting on my subgrade is half of my compressive capacity. This would reflect to a cumulative strain or plastic strain of, let's say, 2%. So this is your EP right there. The key is getting an appropriate representation of how your soil will react under different stress ratios. And then in this chart here, you see that's a correlation between the influence factor and the granular layer thickness H over L for different subgrade stiffnesses. So basically, with your I sub epsilon, which is your influence factor that you got, knowing your sigma D, knowing your dynamic load, the A and the L are just numerical factors that they developed for this method. So I believe the A was zero point 0.5 and the L was 0.15, if I'm not mistaken. And then with this, you do, curve fitting. You see where you fall within these A, B, C, D, depending on the resilient modulus of your subgrade, and then you get your um, granular thickness. And that's basically the combined thickness of your ballast and sub-ballast. Similarly, for mode 2, uh, we're dealing with the same problem, but here we're talking plastic deformations instead of strains. And you follow the same approach. By now, you don't need to touch this because you're dealing with the same track bed. So the beauty is once you have your strain, you can always go and look for your deformation influence factor, and then you can get your granular thickness. Um, Equations here for the plastic strain. The way they deal with the plastic strain is a little bit conservative. If you try and solve the same problem using a finite element analysis, you will realize that the plastic strain is usually conservative because they just link the strain to the thickness of your subgrade material. And again, as a geotechnical engineer, you're the one who can decide on the effective or the depth of influence of your embankment. So how much would your T, like the subgrade thickness, and then you get your H over L as well. In here, they also linked the plastic deformation to the thickness of your subgrade, because the thicker your subgrade is, the more likely that you will need a thicker granular material to disperse that pressure. And that's what this charts are trying to say. So for A compared to G, for instance, right, where you have T over L of 2 versus T over L of 36. So again, you have to always keep these things in mind. uh, Follow like the engineering sense and your understanding of the stress distribution and the factors that would govern your stress distribution. Some of the additional geotechnical aspects now, hopefully that you follow these steps, you're comfortable with your thickness of the ballast slash subballast, you know what granular type that you're going to use. Then comes in additional aspects that as a geotechnical engineer you're expected to have a look at, right? The alignment grading, this is something that you often work with the civil designers. Cut versus fill, how much fill you're happy with or comfortable with, giving how strong or weak your soil is, the subgrade soil. The cut sections recommendations related to like excavation when you have a cut grade versus a fill grade. um, Subgrade preparation, so the compaction, you always need to specify the compaction effort. um, uh, it's always a very good idea to have test pits from like nearby borrow sources, or like locations where you think the soil might be good to be used for backfilling, and have this data within your recommendations, or at least think about them from a sense of like how much compaction you really need, um, the available equipments, and how much effort needed to get to your desired maximum dry density and optimum moisture content. Topsoil stripping and like removal of deleterious material. um, the settlements is also here a significant issue, especially if you're dealing with clay-like materials or soft deposits. So know your consolidation parameters, have enough consolidation testing to be able to assess your OCR values, your C sub C, compressibility. As a matter of fact, the compressibility can actually help you get the constraint modulus. If you do your construction during like the fall slash winter weather, you don't expect your immediate settlement to happen, right? When the soil starts to thaw, that's when you start seeing your settlements. So understanding the timeline and how the construction activities are affected by when you start your construction and when you end it is also very important. um, Drainage requirements, um, very important. Again, often overlooked by geotechnical engineers. Geotextiles is very important to be used for bridging when you have like areas of soft pockets along your alignments, and also to improve your drainage requirements. Um, French drains and peripheral pipes, often recommended, and you should make sure that they are reflected in the civil drawings. Drainage ditches, and the good thing is when you're dealing with a standardized profession, like in railway engineering, for instance, they always have minimum requirements for the dimensions and the width of the drainage ditches, as well as the side slopes to ensure a good surface and subsurface drainage. The last thing you want is, or the least favorable scenario would be water ponding along your rail track or rail alignment. From operational point of view and also from structural geotechnical stability point of view. So you want to make sure that you have like very good to excellent drainage condition all over your alignment. The ballast subballast properties, You have to specify the mechanical properties and the physical properties. The recommendation often includes the gradation. Um, Again, some track standards, they provide guidelines, um, but you can always rely on local contractors' experience, your understanding of the requirements of the project, and you can tweak these gradations a little bit to kind of make it more economic friendly. For instance, in mining sites, you usually have available quarries. And these quarries are crushed rocks that are ready to be used. Um, and and you have to tweak your gradation a little bit to make it reflective of the available quarry that you have on site. Fracture faces to increase angularity and ensure like interlocking friction within your ballast, sub-ballast. The fine content usually very, very low, less than maybe 0.5%. In some cases you're not expected to have any, but depending on the local soil, depending on, again, the project standards, sometimes they allow room for some fine content. So you have to look into that and be aware of how well, good, or typically how, like good or bad this would be for your design. um, so in conclusion, I hope by now you guys have realized that the track bed design is part science, part art. Nothing replaces experience, I guess. So the equations are out there, but again, what parameters you should use, and what's the common knowledge, local experience within your project area will always be a key that determine a lot of your design parameters. Be aware of the applicable standards and regulations when you're selecting your track bed thickness and type. Um, the geotechnical recommendations should cover the physical and mechanical requirements. And I have seen this quite often where the report stops at, here is your granular material thickness, and this is your allowable bearing capacity, and they walk away. But in a projects with the railway projects, this will not cut it, because you need to be more specific about any physical or mechanical requirements that you need for a granular material to be acceptable. So I think by this, I just came to the end of the presentation. And yeah, I hope I gave you guys just a sort of a brief overview of the rail bed or the railway track bed design, and a lot of the aspects from a geotechnical point of view that we should be aware of. Thank you.
Thank you, Ahmed, for this amazing lecture. Yeah, amazing presentation.
Thanks.
Anyone have a question? If you have a question, you can unmute and can talk directly. Okay. So Ahmed, I wanted to ask you, are you doing any modeling, any work related with that, or just go to the empirical equations and?
The modeling is always there and open, but it really depends on the project budget and the client's preference. Softwares like the KinTrack, for instance, that's one of the simple, like, semi-empirical models that you can use to get a sense of the stress distributions that you will get on your soil. I often find it that having a heavily like finite element modeling for this sort of work, unless there is a necessity from a subgrade point of view, sometimes you tend to be to go way over budget. So that's why in practice people always tend to rely on empirical equations experience, as well as semi-empirical approaches if needs be. Yeah.
That's good.
Yep.
Yeah, I agree with that.
So
Okay.
yeah.
Yeah, thank you, Ahmed. Yeah.
Oh, you guys are welcome. Thank you.
Thank you, everyone, and Ramadan Mubarak. Yeah, this is the end of the day. Welcome to you again. And if you have any suggestion, any comments, please don't hesitate to contact me. And thank you for all of the participants. Yeah, have a good day.